Okay, good evening, everybody, and good evening, everybody online. We're live now. I'm very pleased to introduce tonight's speaker, Stephan Jefferis, who's an occasional colleague of mine, and I think, did you say visitor? Visiting fellow at Oxford University, who's going to talk to us about, as you can see on the screen, case histories around chemical and microbiological processes in geotechnical engineering. And I think this is an underappreciated subject, and one that is at the root of quite a lot of disputes, and one I think that our industry in general doesn't really deal with terribly knowledgeably. So hopefully Stephan is going to put that right for us this evening. Stephan. Thank you.
Good evening, ladies and gentlemen. It's been quite a difficult lecture to put together because I'm going to talk about 13 individual case histories. And as I tried to pull them together, I realized that really there was not a lot of connection between them. So I've tried to sort of deal with them by chemical involved, so to speak. But you might wonder why that little fan is sitting in the bottom corner of the picture. We'll come back to that, but you might like to think how it would work if you put a box over it. And it's the sort of thing that sits on the top of a wood-burning stove and just is driven by the heat. What happens if you enclosed it? But before we go there, let's just have a little bit of fun and look at biological processes. And we'll look at the big and the small. The elephants who often charged with sort of creating and shaping the landscape by making tracks that later in the wet season become water channels. But we got a pointer. Perhaps pointers is gone. How's that? Oh, no, that was a failure. Press the white one. Press the white one. There we go. Thank you. Sorry about that. Actually, of course, we should really be using the we haven't got a pointer on the system. So for those benefit of those online, the landscaping picture, actually, those mounds have all been created by fire ants, just leaving a bit of land open. It's a National Trust property, but just see how that you can just see all the bumps and bubbles at the back there, which are just fire ants. The picture of the piece of limestone with what looks like sugar falling out of it, I took that picture in the Temple of Karnak in Egypt, and it seemed that the ants were actually breaking up the limestone. I have not seen anywhere. I have no idea why. Maybe somebody had spilled a can of Coke on a crack in the limestone or something, and they were mining it. But I picked up some of that powder, and it was limestone. Of course, the chipmunk is great at undermining, and the ants, of course, are gluing, shaping, gluing, and grading. They will pick up only bits, of course, that they can carry. So anthill actually has quite finely, narrowly graded soil. So that's the big and the small. Just look at the, for a moment, at the airborne, so to speak. Monterey Island is an island almost shaped by bird guano, bird droppings. That sort of gentle sloping, because the cormorants there nest on open ground, so to speak, and use the droppings in many ways to build the nest. And I suppose, of course, then we discovered that the droppings have lots of phosphate in them, and that can be used as fertilizer. I guess it sounds better, the label on the top right, con vero guano. Perhaps it's better in Italian than saying with real manure, as it would be in English. But then my neighbour's house across the road from where I used to live, the birds would sit on the television aerial. And this happens a lot with television aerials. And of course, their droppings then drop vertically downwards, the black arrow in the bottom left. And what's interesting is that that does create a zone of growth, but it's not immediately beneath the arrow. If you can see the arrow coming down, the roof there is relatively bare, but out to the side is out to the left, no, out to the right, sorry, is a zone of quite significant moss growth. And that's quite interesting that you get these zones, different zones. It's too concentrated, the guano, immediately under the aerial. and it's only out at the edge, it's sufficiently dilute, so to speak. And you will see the same with cowpats and other droppings in the field. And the little note that cowslips are exactly what they say. They're a high nitrogen species. So you found cowslips where the cows have slipped a bit, so to speak. But equally, of course, that picture of the tree in the middle there, that's what cows and other animals, grazing animals, do to trees. If the grass wasn't grazed, that tree would not have a clear understory. It would be completely overgrown. So that is entirely artificial, and probably about 75% of the UK landscape is entirely shaped by animals. And we tend to forget that if we'd stop farming in the UK, we won't have a right to roam, we'll have a fight to roam, because we won't be able to get through the scrub. Land doesn't take long. Some pictures from my holiday in St. Lucia. That's a starfish buried using liquefaction to bury itself. 3 pictures across the top there. They're so perfect that I thought some kid must be going along with a stamp and putting it on the sand. But no, they're real. And how on earth a crab can make those little balls of sand when I couldn't pick one up and keep it intact, and yet it can burrow, carry it out of the burrow. I presume it must be putting some sort of slime on it to hold it together. But quite amazing how, and of course you get the soil mechanic spider, which you see everywhere, little round, little conical holes. This coming down the scale, bacteria, top left, that pink color is biological, microbiological. It's halophilic archaea, and that's an Australian salt lake. On the right, the 2 pictures, I have no idea what's going on, but that was in White Sands in Australia, down in the Margaret River area. Pools, there's a sort of slight dune, and behind water accumulates. I suppose it comes in on a slightly wet, high wave day, creates these pools. The birds then sit on them, drop a load of droppings into it, and these strange, multicolored, very large, and they must be bacterial, I think, but big. I've no idea what the microbiology is there. And of course, the hot springs, if you went to the Reykjavik conference, the Blue Lagoon, they say in the guidebook, is algae. I don't believe a word of it. It's actually hydrogen sulfide, which occurs a lot in the water there naturally, being oxidized to elemental sulfur, and colloidal sulfur is blue. So the Blue Lagoon is probably actually sulfur. And well, we've actually, microbiology in civil engineering, 1990, Peter Howsam was then at Silso, I think now at Cranfield, if he's still there. We had a conference on that 30 years ago, so this is not new. And just for fun, I picked out off the shelf a book I borrowed from the JOLSOC here, which seemed appropriate. I've ringed it in blue there, the microbiology, microbial geochemistry. And we're going to talk a bit about that. So tonight, we're taking a step aside from the usual sort of hard engineering and look at biological, microbiological, and chemical. And we actually very seldom get the whole story. So in some ways, I'm revisiting some stories you may have heard before, but perhaps with some new twists, because investigation tends to stop when you've got enough information to get on with the job, or you decided who's going to pay for the problem. But further testing, no. And try and publish it. I remember I wrote a paper in geotechnical on some of these topics, and the reviewer said quite correctly, well, it really reads like a series of anecdotes. But fortunately, they didn't actually can it. But publication can be difficult. There was also perceived problems of confidentiality. So moving on to the case histories, there's going to be 13 of them, so they're only going to get a very short. So start with a completely simple inorganic one. Smallish tunnel through a hillside, out into open fields on one side, through into a quite large dip on the left-hand side. So it drops, so the tunnel took a water pipe through. There was water in the tunnel, I'm not sure whether that came from condensation or leakage of the pipe. But if we're looking, the background is the wall of the tunnel, looking at where the blue arrow within the tunnel. And rather strangely, it seemed to be built of a single ring of bricks laid stretcher-wise outwards. And the heads were being torn off the bricks. And there was a great pile of debris of broken brick all along the tunnel, which was pretty frightening. And when one looked at it, the blue arrow in the center there, do you see there's some sort of white deposit there? And I think what was happening was that the water was being drawn up by evaporation. There was quite a draft through the tunnel. Air was moving, the water was being drawn up into the brickwork, drawing gypsum out of the brickwork. So I expected that deposit to be gypsum. But in fact, it wasn't. It was a double salted gypsum. And unfortunately, I can't remember. I think it might have been potassium calcium sulfate, but it was a double salt. But that was expanding, possibly just drawing the chemical out, precipitated in the mortar. The mortar then in the ring was expanding, jacking the bricks, and the heads were being torn off progressively further and further into the tunnel. I wanted, if I had to try just closing the tunnel ends to stop the evaporation. Would it have worked? Well, the owner of the tunnel was far too nervous about it and put horseshoe concrete segments in to strengthen it. But it was an interesting example of just water drawing chemicals, which were naturally in the bricks, probably not chemicals from the water, evaporating deposits, but not quite the deposit one expected. You could only tell by XRD what it was, and expanding a bit, tearing the heads off the bricks. So that was a simple inorganic one, water and evaporation. We'll come back to that a little bit with salt deposition in desert cities. Another one that is probably inorganic, foaming of the slurry in a slurry tunneling machine. In Cairo, many years back, the breakout block for the launch of the tunneling machine was through a block of silicate ester grouted ground. And when they advanced the machine into it, the slurry turned to foam. And the foam then just basically, the pumps couldn't work. They couldn't develop the pressure they needed. So the question is, what was causing the foaming? So launched through a block of grouted ground, the slurry is pumped around the circuit, it carries the spoil from the face, the pressure supports the face. And if you may have a low density fluid, you get a low pressure, because in a centrifugal pump, the pressure is a function of the density of the fluid being pumped. So it wouldn't work the hydrocyclones. So what was there in that grout? Well, it was a mixture of sodium silicate and an ester. You need something that will set the grout in a controlled time. Sodium silicate is made effectively by dissolving silica in sodium hydroxide, and the silica-soda ratio is what you look at for silicate for grouting. And then you create this ester, which is basically a salt of an organic acid and an alcohol. And when you mix the sodium silicate with the ester, the alkali in the sodium silicate reacts with the acid in the ester, neutralizes the sodium silicate solution, the silica then deposits, and it releases an alcohol. So the ester neutralizes in a controlled manner. You change the ester to control the setting time. You have different esters with different setting times. There used to be A, B, and C esters, and you have to have enough ester there to make sure you neutralize enough of the alcohol. Now, that particular reaction of an ester and a sodium salt of an organic acid is called a saponification, which you might think, well, that's the answer, isn't it? We've got foaming and we've got a saponification reaction. You might also look at the silicate bit. I can't remember where it was I took that photograph. Some Eastern European country. Somebody can tell me what the writing seems to be possible for a number of countries. That's an advert for the detergent called Persil. You've probably come across Persil in the shop, but did you realize Persil is actually a chemical name? It's perborate silicate. Perborate is the oxidizing agent, the whitening bit, and the silicate is the stabilizer for the foam or the detergent to stop the soil on your garments going back onto the garments. So it stabilizes the soil once it's been taken off. So we've got the perfect stabilizing system and foam generating system. So if you like, at the time, the conclusion was that it was the ester that done it, so to speak. And I rang my friend at Rome Poulenc, who made the grout, Robert Perrichon, and said, it's your grout that done it, you better tell us what to do about it. And he said, well, I'm not sure it's the saponification. And but he did say you need an anti-foam and I would suggest this. So we got a barrel of it. And fortunately, somebody had a barrel of it out in Cairo. So they got it and we put it in the system and it sort of worked. We muddled by and got the foaming machine launched. But was it the ester that caused the problem? So years later, we come to a caisson excavated down through grouted ground. This was going to be a compensation grouting job, cement grouting and silicate ester as a secondary grout. And I was called in because there was a terrible smell in the caisson, really, really grossly unpleasant. So, and people were falling ill, some with septicemia and other things. I think the septicemia was a completely different issue. But by having that alcohol in the grout, you've put in a mass of organic carbon into the ground, which bacteria might like to work on. And I think what was happening is the natural sulfate in the groundwater, plus the alcohol as the carbon, plus bacteria, was being converted to hydrogen sulfide. But the other thing that can happen with organics like that is that you may have a different sulfide. The R in the RSH there means any organic group. And the RSH group are what are called mercaptans. And they're some of the smelliest things known to man, so to speak. I think butyric acid is probably the smelliest, which is sort of neat essence of landfill. Why is that? Because we're designed, I believe, not to want to eat or go near rotting materials. So mercaptans and butyric acid were incredibly sensitive. So it was no wonder people were falling ill. And I think it was probably the mercaptans rather than hydrogen sulfide, because frankly, if it was hydrogen sulfide, they would have been dead, because hydrogen sulfide is more toxic than hydrogen cyanide. But I remember we had a sample of that, and I was thinking one evening, hang on a minute, I wonder if it's also breaking down the carbon to methane and carbon dioxide. So I shook the bottle out, opened it, and put a match to it, and it would flare. But hydrogen sulfide is flammable, so I put some iron salts in it to precipitate the sulfide, left it for a few days. So I went back to the owner and said, I think you've got problems because you've probably got several tons of methane in the ground as well as the mercaptans. They did nothing. Fortunately, nothing blew up, but it was bubbling up into a tunnel above. So it was quite a lot of grout. But why did that happen? Same grout, but a very different problem. Now we've got smell, hydrogen sulfide, methane. And actually, I went back and reopened that bottle about 5 years later, and it flared again. I must find it and see if it still does. So the reason may be that they had problems was that when they formulated that grout, they didn't realize they needed to put in a surface active agent to mix the ester and the silicate. They're not miscible. They separate. So you put a detergent in a properly formulated grout just to try and get them to mix. If you don't, then there's a risk of them separating. And I wonder whether that was the issue, that the Rome Poulenc grout that I spoke of in the previous case history would have had that foaming agent in it. So that could have caused the foaming of the tunneling slurry, not the saponification reaction. It was a deliberate foaming material put in the grout to stop what happened in this case history. But this case history was about 10 years later. So you could say that the silicate ester reaction was a saponification in name only. And in fact, somebody actually went and had a look and it doesn't foam, that particular reaction, so without the addition of the foaming agent. So here we are. I think one of the things about case histories is go back and have a look at them when you get new information, because it may allow you to reinterpret. But what it also tells us is that we've got microbiology at work as well as just straight inorganic. So I've given you a couple of little inorganic case histories, but one of them then leads on to microbiological processes, which one wouldn't have guessed were going to happen in a straightforward. But before we go into the microbiology, we better get some basics. Chemical reactions, if they're spontaneous, release energy. That's what makes them spontaneous. Living organisms require energy. Energy for survival, just ticking over, so to speak, and energy to grow. So there's got to be a source of energy. And basically, there are two sources of energy: light and redox reactions. The sun is going to be the major source of light, of energy, if you like, for all plant growth. And we as air-breathing species rely on redox reactions, moving electrons around. Now, what on earth is a redox reaction? Well, think of pH. pH is about acid, it's about hydrogen ions. Redox is about electrons. And if you think of H plus is just a proton, we're thinking about the electron. So we're thinking, if you like, of the other side of this pair, proton, electron. And redox is all about this electron transfer. That's where the energy comes from, the electron transfer. That's what light does, it enables transfer. But these transfers have to be balanced. If there's an oxidation, there has to be a reduction. And very often, where the electrons end up is on oxygen, as oxygen 2 minus. So it's called the terminal electron acceptor, typically. Well, we're not going to go any further into the chemistry, but we need to know about redox. So a few more basics. Life, if it can move, will go where the food and energy are. If it's sessile, like we were in lockdown, you need a flux of energy and food, which Ocado and Sainsbury's and other supermarkets are available, which will deliver to you. And if it can, life will stay where those are available. If you're a bug in flowing water, then you've got to be in water that's got those available to you, and you're likely to need to have a little mechanism of movement. If you're sessile, you probably may put out a slime to stop you getting washed off and going off downstream. And of course, greater fluxes, greater populations. So you see biological clogging. Because there's food available, you can grow more. So basically, if you've got flow, you're likely to get a bigger population of bacteria. But it will seldom be a single species. They live in consortia, passing materials one to the next. And just remember, almost all the soils we're going to come across were laid down in an anoxic environment. Oxygen was very much a late comer, wasn't it, in the geological history? And if in soils, of course, there's no light. So the only available energy in soils for microbiological life in soils is redox reactions. So that's the crunch. We've got to look at these oxidation reactions. They are what are going to power any microbiological change, like the generation of mercaptans. But one of the problems is they can be delicately poised, means they can balance one way, balance the other. They can be reversed. Other microorganism can come along and use that to go the other way, provided there's some other energy source to enable that. A little bit of notation. The P symbol in chemistry means minus log to base 10. So P of X is minus log to base 10 X. P of H is minus log to base 10 of H plus. And P of E is minus log to base 10 of the electron activity, except we can't measure that, but we can measure a relative electron activity. So we have the relative electron activity. So taking an oxidation reduction process, just burn a bit of sulfur, S plus O2 to SO2. But if I actually put that in terms of what the electrons are doing, sulfur elemental, 0 valent, O2 minus, 0 valent. You put in the nominal valencies that you're taught, if you like, back in early days of chemistry, and that ends up as S4 plus and two oxygens, each 2 minus. Sulfur is a really complicated species because it can take actually almost any valency from -2 to +6 and some fractional valencies as well. So it's a really good one in the ground. It can take on an immense number of states. So definition, oxidation is loss of electrons, reduction is gain of electrons. The one we all know about from water wells is iron 2+ soluble going to iron 3+ plus an electron. Don't forget that electron's there. That electron's got to go somewhere else. It can't just float around in the environment, but that's an oxidation. So what we can say is we actually relatively seldom meet a strongly acid or strongly alkaline soil. They're pretty well buffered. If you put acid on soil, it'll find something to react with. If you put alkali on soil, it'll find something to react with. If all else fails, it will react with carbon dioxide from the atmosphere. So we don't really see massive shifts of pH in many soils. Okay, there's acid mine drainage, which occurs in a lot of tunnels. But actually, it's much easier probably to change PE, that redox measure. But have you ever heard of it? Well, you have now. So what do? Well, we breathe. It raises our PE. And the ground does it too, as a result of atmospheric pressure changes. And the way we as engineers, civil engineers, geotechnical engineers come in and change things is by dewatering, lower the water table, lets air in. Tunneling, if you're above the water table, you're letting air into the ground because of atmospheric pressure changes. Flooding, keep the air out. We've changed the redox. Grouting, block the ground, also may end up putting a lot of organic chemicals in. If we add carbon, then we change the PE. So as geotechnical engineers, we change the PE of the ground far more often than we change the pH. The only thing that really we do that changes pH is grouting with cement grouts. So what happens if you change PE? Well, the answer is it may be problematic. It may take a long time before that becomes evident, but it may persist then for a long time. So message, and I put a few of these sort of diagonal stripes, message, processes in the ground can be slow, but they persist. And then you can draw up PE pH diagrams. There's lots of these around, books of them for different mineral species, but basically, if you plot PE against pH, you can get two binding lines, binding domains, the red and the green. If you try and go below the green, you'll evolve hydrogen. If you try and go above the red, you'll evolve oxygen. You break the water down, basically, which is what the life we live in. And that green strange shape in the middle is basically the area where most soils lie. Well, isn't it great just within that sort of relatively bounded area? But unfortunately, that, of course, is the whole of life. So it doesn't really restrict things very much. So what chemical species are we likely to come across? Well, if we look at the yellows, which are the major essential for all life, then hydrogen and oxygen, well, we know those are going to be in the ground and may or may not cause problems. Nitrogen, we do find problematic in the ground. I'll give you an example. Manganese, they're major biological transition metals. Iron, sulfur, carbon. And I'm going to talk about arsenic as well, but those ones in the red rings, if you like, are the ones that we're most likely to meet as problematic elements in the ground. If we just took an organic material and closed it up, no oxygen available, what state could it be in the oxidized and reduced state? Nitrogen can be in ammonia or nitrate. The bacteria are going to decide, the microbiology will decide which of those it is. Manganese can be soluble or insoluble. I've met a manganese slime once. They're pretty rare. I'm not going to give you any examples tonight. And regularly, of course, we have problems with soluble, insoluble. Sulfur, we talked a little bit about hydrogen sulfide. Sulfate damages cement. and of course that problem of pyrite oxidation. Carbon in landfill, methane on one side, carbon dioxide on the other. Arsenic, mass problems, of course, in the Bengal Basin with the deeper wells there. And I'll give you a more complicated example of arsenic. But if you just sealed up a flask of organic material, then we would see various species being lost and various species being produced. And they tend to occur in the order of losing oxygen, losing nitrogen, manganese, iron, sulfate, and carbon, generating the species produced water, ammonia or nitrite or elemental nitrogen, manganese reduced, gone into solution, iron reduced. So there's an order to which these reactions occur, and they may not occur simultaneously, but if they occur in time, they can also occur in place. If we think of reactions spreading out from a highly reduced area where there's been spill, say petroleum, out to an oxidized area where the groundwater is in equilibrium with atmospheric oxygen. Well, it won't ever probably achieve quite that, but that sort of order, but it'll spread out. So we'll get all those different species occurring at different positions out from the source. So the effects may vary with time and position. And the message really is that a single source can lead to lots of different chemistries in different places, but you may only ever see one of them because you haven't looked for the others. So it's not a bad idea to keep in mind, but what else is happening? And also remember, if we're looking at an oxidation or reduction, you've got to find the other half. Where have the electrons gone, or where have they come from? So, recap a bit. Don't think of a single microorganism, a cooperating system carried out by a population, so to speak, especially when you get into the more complicated things like sulfate reduction or sulfate oxidation, sulfide oxidation, and methanogenesis. But let's come back to this beastie. What would happen that you sit that on top of your wood burner and it's meant to, the fan turns just from the heat. If you put a box over that so as to enclose it, what would happen? Would it carry on running or would it stop? It stops because what's happening, of course, is that the heat is being conducted up the stem. The stem's there to make sure that the little thermopile in the middle where the red and black wires are doesn't get overheated. And then the heat sinks at the top, the fan blows over them and cools them. So you've got a temperature differential across that thermopile. And it's an interesting thought that as the fan goes and cools the top more and more, does it go faster? Because you've now got a bigger differential. But that works because there's a differential. And life needs a differential. And so where are we going to find it? In tunnels, in basements, in dewatered areas, where we've let oxygen in for the oxidations or for reductions in marshland. Remember, I said it can go on for a long time, in grouted ground and in desert cities, but that's a bit special. But basically, equilibrium is death, but it may not be achieved for a long time. Thank goodness. But basically, you need that driving potential. So let's get specific. Nitrogen. It sort of goes against school chemistry, doesn't it, to think of something like ammonia changing in the bottle, as it were, going to nitrogen gas or nitrate. You think you've got it in a bottle sitting on the shelf and it should stay there like that. But if you put some food into the bacteria, well, it's not like that. Notice there's a gap between ammonia and nitrogen. It would be wonderful if one could go from ammonia to elemental nitrogen and get rid of all that ammonia out of landfills. It's nitrogen gas. As far as I'm aware, there isn't a route to achieve that microbiologically, or certainly not readily. And so if you want to go to nitrogen gas, you've got to go from ammonia to nitrate and then go back down again. You've got to go up to go down, the nitrogen chemists say. And in ammonia, remember H is plus, so H3, That's 3 pluses. Ammonia is 3 minus. And nitrogen in NO3 minus 1. Sorry, I've just had a cataract operation a few weeks ago and I've had difficulty focusing, and is oxidized +5. So there's 8 electrons to play with the nitrogen. So let's look at where we might meet nitrogen in the ground. Shaft, I've had this problem a couple of times, or 3 times actually. Shaft adjacent to a river, excavated through jet-created ground. One of those special occasions where we do change the pH of the ground because of the high pH of cement. It's a silty soil, shaft depth 12 meters, shaft diameter 4 meters. Deep soil, no oxygen, there's nothing that generates oxygen in the ground. Some organic material, small amount of nitrogenous material, and you could say it's just a typical average riverine, estuarine, muddy material. Soil analysis, organic matter, 0.6% in one, 1.5% in the other, nothing exciting. Ammoniacal nitrogen, that's nitrogen in the ammonia form, 0.03%, 0.15%, really at the trivial level if you were asked to look at the chemistry of the soil, so to speak, without prior warning. Loss on ignition, nothing spectacular. Moisture content, rather different between the two, but nothing to really alert to a problem. After jet grouting, because it was jet grouted columns to form the shaft that was then going to be excavated out the middle. pH of 12.4, not unusual, 10.7 in one of the others. Oops. What's going on? We've got strongly alkaline material from the cement, plus ammonia in the soil, probably absorbed onto the clay, goes to ammonia gas plus water. That's what happens when you put ammoniacal materials in a high pH environment. Then, of course, the ammonia comes off as gas, and the slight warming of the ground as a result of the hydration of the cement helps to drive that gas off. If we look at the numbers, the control level for ammonia in the air is about 20 ppm. You'll notice it at that sort of level. To fill that shaft with ammonia to that level, it's a mere 2 grams. There's 4 kilograms of ammonia possibly released from every cubic meter of soil. So 1 meter cubed of soil could produce 40,000 ppm ammonia in the shaft. That shaft was abandoned. It was just simply impossible to work in the shaft. So be a little bit cautious. This isn't going to happen very regularly with jet grouting. I've only met it 3 times. Once was the reference to the Singapore job, where the ground was actually at 40 centigrade because of the heat released from the cement. So, message, solid to gas transformations, which quite often occur with, or liquid to gas with redox reactions, sulfur to hydrogen sulfide, nitrogen to ammonia, can be seriously problematic because gases, of course, immediately gets into our system and is very, very low density. So let's look at that one, that the Old Street sulfide pyrite oxidation, which I've spoken about very often, but again, just revisiting some of the issues there. Pyrite in the ground, tunnel through the bottom of the London clay, where there's some pyrite in a slightly silty ground, produces sulfuric acid. But the odd thing about this particular tunnel is that instead of the acid dissolving the lining and causing the tunnel to come, the tunnel to, if you like, come inwards, it was actually growing at the crown and shrinking at the axis. It was being pushed inwards rather than squatting if it was being weakened by acid attack. So, that's basically that's it. The lining all cracked, and that's it strapped up prior to it being replaced. It was over tunneled. What seemed to have caused the cracking was they were monitoring the stresses in the lining because they knew the tunnel was squeezing in at knee height and being pushed upwards. And they put some strain gauges on the red boxes there. onto the webs of the cast iron segments, and the drilling and tapping of those led to a little bit of crack initiation. Then one ring cracked, and then the next, and then the next, and then they strapped it up. But the acid, pH of 0.7, pretty low. That was extreme. Sulfate at 200 grams a liter. So the hypothesis was that we had a ring of contact grout outside, and that was reacting with sulfate generated by the pyrite oxidation. And it's quite interesting, when they over-tunneled, they exposed some of the clay behind the lining, and those yellow streaks, I'm almost certain, are the acid, where the acid has moved. It's quite dry. It's interesting. Whether it was sort of seasonally wet and dry, I don't know, but certainly it wasn't a homogeneous flow. It was very much localized. So what's going on? Air driven by atmospheric pressure enters the soil. Pyrite is oxidized to sulfuric acid, or sulfate, let's say, plus acid. And that reaction is microbiologically accelerated. It's very, very slow. You can have a lump of fool's gold pyrite on your desk, put it in water and leave it there for years and nothing will happen. But if you put some bugs in, one step of the reaction is catalyzed, and that makes it go much faster. The acid, as I said, finds lots of material in the soil to react with. So it's not the acid, although pH 0.7 has been reacted with an awful lot of soil as it made its way to the tunnel. The sulfate has had nothing much to react with. So it arrives at the contact grout as a little bit of acid and a lot of sulfate. So basically we get sulfate reacted material and a very small amount of acid reacted material at the contact between the soil where the acid is coming from and the contact grout. The contact grout was about 3-4 inches thick. By chance, I found a lump of it a day or two ago. And then there'll be unreacted grout, the contact between the segments and the grout, or there would be in places. And that was still strongly alkaline, and yet we know this process had been going on for 50 years. But the sulfate expands the grout, and that was what was happening. The grout was being expanded. It was happening mainly at about knee height because that was where the water seemed to be. It was a relatively lower permeability zone, and the water was flowing across. The acid was reaching the grout at that sort of level. The tunnel was then over-tunneled and relined with stainless steel. And we'll come on to the stainless steel in a moment. But that same reaction, the reaction of sulfide, oxidation to sulfate, is of course the problem we see with lime-treated soils as well. So let's just begin to pull a few things together. We've got reaction fronts, and they're seldom simple. We need to consider the mass balance of those chemical interactions. How much acid, how much sulfate, how much whatever. And we need to think about the clays as providing ion exchange and quite a lot of chemistry there. And it does mean that reaction fronts can be retarded. The acid front is moving much slower than the sulfate front. The sulfate front expands. Years later, the acid will get right through and dissolve much of that grout, and the tunnel will then collapse outwards once we've got a void outside. But to begin with, it's being squeezed inwards by the sulfate. The acid comes in maybe a couple of centuries' time, except we've taken it away now. And there's a little detail there. If local equilibrium isn't achieved, say it can move faster, the reactions, the actual reactions with the ground are slow, then that reaction front can move faster, but that's a detail. Heave of line stabilized soils, that's just really same reaction, different problem. We know all about this, stabilized soils. It's very economic process, mix lime and clay, you get a good strong material. The crystals form a needle-like habit of reaction products between clay, sulfate, and lime. They can also take a colloidal form. There's lots of guidance, But one of the problems is if you've got, say, gypsum in the soil, which it can be quite large but discrete crystals. So you can't just do a chemical analysis. You need somebody watching and looking. Pyrite may be missed. Say you've got a sloping site. You do a site investigation, relatively shallow auger holes, but then somebody comes in and cuts into a hillside. The deeper soils, no oxygen, pyrite, not sulfate. That pyrite then oxidizes, then you get problems. And it may be all been mixed together, left to mature in a pile, and then been spread across the site. So you can still get problems, despite a lot of advice on this, but it's the same problem now. It's microbiologically mediated at Old Street, but is it microbiologically mediated in lime stabilized soil? The pH of a lime stabilized soil is so high that bacteria are not good in alkaline environments. They're much better in acid. They can live quite happily at 0.7, but up at 10, 11, 12, the cell wall likely to be broken down. You lyse the cell wall. So I don't know whether it's microbiological. I'm sort of suspicious. The chemical reaction, lime plus sulfate plus clay, actually may end up with a net slight shrinkage overall. The thing that causes the swelling is the way the needles grow, jack the system apart, or the colloidal material swells. And it seems that either water is essential for that reaction or flows in to fill the vacuum created, the void created by the needle-like. They're little like props pushing the soil apart. They're actually, most chemical reactions that we see and produce a slight shrinkage, like the setting of cement. But this one produces expansion by pushing mechanically the soil apart, and water fills the voids. So if you want to know whether it's swelled or not, the easiest way is just to measure the moisture content. It gives you a brilliant example. There's no actual need to, and I'm not convinced about the current advice on how to do those tests. Interesting, that heave often occurs after the first autumn rains. We do this, the lime stabilization over the summer period when it's reasonably dry, get that first bit of rain, boom, and it can almost come up overnight. And the lime stabilized layer can almost double in thickness. These are big movements. 100 mil, 200 mil, 300 mil, not a problem. Number 6, the reaction going the other way. I'm going to speed up, haven't I? Sulfate to sulfide. This was a car park, deep basement. Reverse reaction. Remember, they're delicately poised. So what we've got is the deep basement. There may be some heave, the pile basement, maybe some heave. So you put a void former in, down comes the concrete slab cast on top of that void former. There's a sump that collects water if it collects under that void, pumps it up the surface. Every time that water pumped out, there was a massive smell in the street. Hydrogen sulfide was released. So we drilled some holes through the floor slab and then went to inspect. We had no idea what we were looking for, except we knew the soil was pyritic. So that was a sort of confounder. But hang on, it's already in the sulfide form. Why we can't get hydrogen sulfide? So basically, we sort of put a jam jar down through the holes that were drilled, collect a bit of the water, put a lid on it, shake it up, sniff it. We didn't know how toxic hydrogen sulfide was, and mapped out the floor where the problem seemed to be. Went out to lunch, had a pint of beer, as you could do in those days, came back, thought we'll just check. Couldn't smell a thing. Total nasal fatigue, or maybe one pint too many. Desperation, put my hand down through one of these holes and pulled up a bit of the cardboard, which was a nasty slimy mess, but with big black dots on. Sulfate reducing bacteria are black, or can be. It was just simply sulfate in the water, carbon source from the cardboard, reduced to hydrogen sulfide, stoichiometrically, almost exactly all the sulfate was going to sulfide, and seal the borehole, end of problem. Delicately poised. But what was interesting was that actually there was another case reported about that time where it was a basement swimming pool, I think, and they lifted up one of the inspection holes and somebody wanted to have a look down and they lowered a cigarette lighter down to have a look and it went bang. And there they got methane. We didn't know that at the time on that Cambridge one. And I wonder whether there was methane there, but we just didn't know about it. So maybe it was bubbling methane off, but we don't tend to get these things occurring at the same time. So whether it was methane and hydrogen sulfide, I don't know. Another problem is that if you get anoxic systems, like say the iron slime on a dewatering pump, stainless steel is not good in an anoxic environment. Stainless works because it forms a passive oxide film. If you cover it in slime, then you can get pits in the in the metal. So at Old Street, the question is, could we have niche environments where the sulfate was going to be reduced to hydrogen sulfide? And we'd already bought the stainless because they got a good deal on it. So the only way to keep the sulfide forming was to keep the carbon out. So it was a very strict control, but there was carbon in the ground. Iron reducing bacteria, a whole lot of iron oxidizing bacteria around the world, Australia, India, UK. Just one that I might just highlight to you. That picture is the iron being oxidized in the spilling water out of a landfill. Do you see that slight iridescence on the surface? You'll often see that in boggy areas, and you might think it's oil. It's not. It's iron hydroxide on the surface, because if you prod it, you can break it. Whereas if you prod an oil film, it'll stick to your finger. So you can get reports of oil in some of these waters. It's not, it's iron oxide. But what can that iron hydroxide do? We're on to number 9. There's hope yet. I might keep the time, John. Railway tunnel in London changed hands, and people were interested in the iron slime in the track bedding. It was just a nasty nuisance on the wheels of the trains. And then somebody analyzed it. And then things really got to be worrying, because what could go wrong? Well, the iron slime is a very effective sponge for anything chemical, and it'll absorb arsenic, phosphate, heavy metals. It's a really it's a bit like activated carbon, activated charcoal. You've got activated iron slime. So a leak from showing the green down the side of the tunnel, water leaking in, slight amount of iron in it. Again, we didn't really get a proper iron analysis. Problem solved. Don't bother to do any more further detail. Building a slime, and then the slime was filtering that water and removing from it arsenic. We estimated that the arsenic concentration in the water was about 10 micrograms per litre, not milligrams, micrograms. But the flux was 1.8 kg a year. And that was all getting trapped in the iron slime. The phosphate, probably about 5 milligrams a litre, 5,000 micrograms, 880 kilograms a year potentially absorbed onto the iron. And the iron itself, we were getting 88 kilograms of iron being deposited into the slime. What was interesting, we didn't realize at the time, where we probably got much worse analysis really near the source than further down the system. But the arsenic was the problem, that when they analyzed the slime off the wheels of the trains, it contained arsenics, which was a bit of a worry. But actually the antidote to arsenic poisoning is fresh iron sulfate solution. So perhaps it wasn't quite as bad, but I don't know what they did. They probably sealed off the leak. So small concentrations, large accumulations. Just a few nearly closing. Carbon. Carbon's quite interesting because remember I said you've always got to have an oxidation balanced by reduction. Carbon disproportionates. Part of it goes to carbon dioxide oxidation, part of it goes to methane reduction, which is why in landfill gas you get roughly 50-50 of carbon dioxide and methane. That's what the bugs do. That little picture of a field and a hedge looking rather sad is not just because something's a little bit toxic there. It's because methane is leaking through fissures in chalk underneath from a landfill about 500 meters away, and it's coming up under the road and coming up into the crop and asphyxiating the roots of the crop. They need a bit of oxygen too, and asphyxiating the roots of the hedge. A few little pictures. I've reproduced the picture of the dead area of crop. You would not have a clue that that hedge and that crop were killed by methane asphyxiation unless you knew the landfill was there and unless you knew there was chalk, fissured chalk. So top left, bubbling up methane from a landfill, not that landfill. Top right, quite interesting, a cherry orchard where all the cherry trees, slightly deeper rooting, have been killed by methane, but the grass is growing luxuriantly. So the diametrically different top to bottom there, one you've killed the grass or the crop, so to speak, one you've not. But the thing you rather seldom see is that when methane leaks out of a landfill or something like that, it can be naturally oxidized to carbon dioxide, which is the picture bottom right there. It's a brown color, pink to brown methane oxidation. If you're in a tunnel and you see a pink slime, get out, because methane oxidizing slimes tend to be pink to brown. So you've got methane leaking in. So that would be steaming in wintertime. You'd see steam coming out. So look for some steam seeps. Very quickly, very big problem of rising groundwater in many of the desert cities where people like to water their gardens and their parks because a green city looks so much better. And of course, also mowing the grass cleans up all the debris. If you've just got miles of sand, the debris tends to collect all the litter. It's interesting, I was working here in the Kuwait Institute of Scientific Research for a while, a few weeks, and wandering around their parking area at lunchtime, that's the flowers, and alongside each individual flower, there's a watering point. And we are working on rising groundwater due to overwatering of the. And of course, you can get salt. Now, actually, they water their parks as relatively saline water. So I couldn't be sure that that tree, whether the salt deposit there has come up from the ground or whether it's just evaporation of the water. But that on the top right is a pillar of salt. If you like, the biblical Lot's wife, that one was growing on a can of Coke. It was about 200 mil high. Salt water can climb up on the salt. The surface tension increases as the water gets more saline, and then it can climb up on the deposited salt. So you really do get pillars of salt. And of course, night, day, wet, damp, humid evenings, you can get salt dissolved, crystallized again in the sun. And what's happened, bottom left there, those are about 5 meters apart, concrete fence posts. They look quite close together. I know they're fence posts because in one of them you can find a little bit of the remains of the reinforcing steel in there, but completely destroyed by wet, dry dissolution, crystallization, dissolution, just a little piles of debris. And bottom right is the face of a concrete wall blown off by salt deposition behind. The salt got into a crack, wicked up, pushed it, wicked up, pushed it, boop, and slowly completely destroyed. So that's just the effect of too much water when you've got salt in the ground. Water and add a bit of detergent. This was in Nigeria. The detergent seemed to have a completely dispersing effect on the local clays so that the ground was just collapsing wherever there'd been a leak of detergent. And it was the very dilute detergent that seemed to do it, and particularly the detergent precursors. And the collapse front was just propagating down so that the buildings with deeper foundations were affected later. They were mainly strip foundations, but the deeper they were, the longer time. But water alone did not do it because it was a large water tower that had been damaged in the Civil War and had been spraying water out for a long time without any collapse. But a bit further away, where people had been washing their hands after working in the detergent bar factory, had created a lake from the detergent just washed off their hands from a fire hydrant, caused the ground around to collapse. And all the drains were collapsing too because of overspill. The ground was collapsing. And they had to repile. I'm never quite sure which bit was the original ground level, but the difference in level where was the sort of amount of settlement. And some of the metal frame buildings, the straps, one way were being compressed and buckling, and the other way were in tension and snapping. And occasionally you get a great bang as one of the straps snapped. But if the chemistry isn't enough to worry you, let's just have a look at this very happy little building built on a landfill, piled, so there'll be no problem with settlement. But if we look there, there's just that little white cuff on the bottom of the downpipe. The ground has settled that much. One wouldn't have known, except that whoever needed to put that cuff on the bottom of the pipe, because the ground had gone down that much, hadn't got a bit of brown plastic to put on and got a bit of white brown. Perhaps no harm done there. But what about if we look a bit there, the inspection chamber is popping out of the ground because it's quite rigid and the ground's gone down around it. That's now a trip hazard. What about the gas and water pipes, the electricity cables into the building? So very quickly, how are we doing on time, Don? I'm a minute over. Evolving problems. I think we're going to have problems with recycled materials if we're not careful as a community. Because, okay, it avoids landfill and somebody else takes the blame for the carbon dioxide emission, and there'll probably be fewer haulage miles. So it must be sustainable, of course. But what happens when it goes wrong? The reason we're always accused of being a conservative industry is because we like to know whether materials will work. And some of these materials are being quite rapidly pushed on us. And there is guidance out there. But does it really address the problems about performance in service? Very often the guidance is about, is it going to cause an environmental problem? Is the leachate all right? And in fact, even this document on groundwater, I believe, doesn't properly address the high pH from crushed concrete and things like that. So I think we need to rethink some of the guidance to focus it on operational, not sustainable environmental bits. We need to get our side of it, the user, and we need to be clear who's going to pay the bill if it goes wrong. So just very quickly, ask yourselves, have you used recycled materials? Have you had problems yet? Do you want to look backwards as well and see what problems you might have left behind? So who owns the problems if something goes wrong? Say you put crushed concrete in for a working platform and you've left it there. Is it going to cause trouble? Well, crushed concrete is strongly alkaline and that pH will remain high for a long time. And the Environment Agency will probably get worried at pH greater than 9. Crushed concrete will have a pH 10, 11, 12, no problem. Certainly above 9 for years, probably decades. And of course, it's very sensitive to sulfate attack. Once you've crushed it, the guidance we have is for intact concrete, crushed concrete. Well, there is guidance now. Also, what happens if we mix crushed concrete with soil because it's been used and now we've got to dispose of it when that building's knocked down? We've now got a high pH material that we can't just call as crushed concrete. Are we going to have to take it to a toxic waste landfill because of its high pH? Possibly yes at the moment. Incinerator bottom ash is, I went just the other day to have a look at our local incinerator to see just how big a mountain of ash there is there. It's not very big at the moment. It worries me. Where's it all gone? Because that incinerator takes 300,000 tons of material a year. 200,000 tons go up the chimney, 100,000 tons of ash and debris. That's gone in construction work somewhere. The Environment Agency will want to know where you're putting it, but they won't tell you perhaps about its potential to heave, its potential to evolve hydrogen. It's lovely stuff. It self-cements to a certain extent, but it can swell when it's moist. Sulfate attack, well, there's now guidance on sulfate attack of crushed concrete. Basically, class 1 is the best. You won't get any better. And that's some bits of crushed concrete that have been in contact with sulfate, just sulfate lying on sulfate soil for about a year or two. Quite interesting, bottom right there, that's a bit of slag concrete, slag cement concrete, the blue color, and it's survived. The dust around was all lumps of concrete, but just sulfate. So we are, I think, at risk. And the problems of incinerator bottom ash, the aluminium foil you happily wrap your cooking in, when that gets into the incinerator, it's going to be melted, almost impossible to get out of the ash. Ash is slightly alkaline plus aluminium gives hydrogen. Major new development, gas man installs or checks the gas main, checks there's no leaks, discovers gas under the floor slab, thinks it's him, checks again, finds it's actually hydrogen from the incinerator bottom ash. That's the sort of problem we're going to see, where it'll be discovered by accident, but it's gently evolving. That methane generated by the void former and that project, they sank a shaft adjacent to the building and tunneled underneath to remove the slab. They might have had to do the same in Cambridge if we'd known it was could have been there, but we didn't. So the aluminium is a major potential risk. Also, it can cause a heave when it reacts. And basically, if you want to check, they got much better at getting rid of the metals, but take a bit of the incinerated bottom ash, just simply put some sodium carbonate or sodium hydroxide on, see if it fizzes. If it does, you know you've got a potential problem. So basically, to summarize, problems, and I think I've shown you, are very context specific, so very rare. But we've seen just water, evaporation, and precipitation can cause problems. Oxidation reductions are going to be the major processes in the soil. And all those species that are essential to life are going to be potential candidates in the ground, particular sulfur, nitrogen, and manganese, and arsenic, if you like, as a secondary, if there's iron oxide. And iron oxide can concentrate. Injection of grouts or chemicals, you're going to more likely, except for cement, change PE than pH. Soaps and detergents, well, we don't often meet problems, but those particular laterite soils are incredibly sensitive. And I've had that problem with laterites a couple of times. And just think about bugs. They change the chemistry. It's not the chemistry you started with. And the problem with all these ones is they're very difficult to predict a priori, because you may have no clues there's a problem there. Thank you all.
Thank you, Steph. Phil, I've just asked Phil to distribute a microphone internally here in the room so people can hear any questions online. So I think, can't walk away from the mic. Stephan, I think you've frightened everybody sufficiently online that nobody's asked any questions so far. So if you have any online, please put them in the chat. I've got one slightly frivolous question: is have you returned that book to the Jolsock Library? And another really is, for me, before everybody in the room gets a go, is the issue with, I've got some mystery settlement problems at the moment. The issue with the detergents, is that specific to particular types of soil?
I think the answer there is, I wonder. The laterite, I first met it where it was the detergent precursor, and it had caused localized collapse and also erosion. It seemed to disperse the soil, so the soil was eroded. And the lab had taken some of the soil, some kaolin, mixed it with the detergent material, then filtered it on a filter paper, and it had all passed through the filter paper. It was that fine It was that finely dispersed. And they'd assumed then it had been dissolved. We said, well, no, that's not possible, but it could be dispersed. So we did some tests. And yes, it was dispersing, but it seemed to collapse the soil. I don't know. It may be the iron is particularly in the laterite is particularly sensitive to dispersion. But I think some of those mountain villages where you get collapses in sort of Italy and places like that, I wonder whether leaking drains aren't responsible a bit. But whether we see in the UK, I've never seen it reported in the UK, but twice in Nigeria, different parts. So I think it's certainly the whole essence of a detergent is to disperse. That's what they do. It wouldn't be a surprise if they disperse the soil.
Thank you. I suspect nobody's reported it because nobody's thought of it apart from you. So thank you. Well, any questions in the room? So, David Hartwell. Could you just introduce yourself, David, to the people online before you ask the question? Thank you.
David Hartwell, retired, brackets, brackets, brackets failed. Steph, great stuff. 2 questions. You talked about the old street and the stainless steel lining and the concerns with that associated with carbon, I think you said.
Well, basically, we've got sulfate and acid there, but remember the sulfur reactions can be delicately poised. They could go back to being hydrogen sulfide. So the sulfate could go back in niche environments if you provided organic carbon. Because one of the great debates, elaborating a bit, was what on earth to put round the tunnel as the contact grout when they over tunneled, because cement was obviously going to react with the sulfate. If we used an organic grout, we put a lot of carbon in there, that then might be used by bacteria to reduce the sulfate to hydrogen sulfide. Hydrogen sulfide would then strip the passive oxide film off the stainless steel, and then it would react quicker than mild steel with the acid elsewhere. So you can get niche environments. Bacteria don't work globally, so to speak. They can also work in niche environments. So niche environment, bit of carbon, sulfate, not try and get it not too acid, because the sulfate reducers don't really want to be too acid. So if you've got a niche environment where it wasn't particularly acid, you could get hydrogen sulfide, then you dissolve the lining, and you get that same process happening underneath slimes on dewatering pumps if they get covered in sulfide. So it was basically, in some ways, stainless steel was not the right material underground because its resistance to acid requires oxygen. So, and I gather it's rusty there, but
so. Are we incorrect in all the submersible pumps we use are almost universally stainless steel?
Isn't it?
And the Rolls Royce of well screens are stainless steel.
If you've got iron slimes, perhaps not. But you need a little bit of acid to dissolve the material. So if the water's pH neutral, then the stainless probably won't be attacked. It was a combination of acid and something that strips the oxide film off.
And as you say, most groundwaters, soils and groundwaters are relatively benign.
That's so we don't see problems, but it's not. And what's the oxygen content of the groundwater? If you're getting precipitation, it's probably slightly oxic, but that's because that pump I showed actually had pinholed through. Can't forget, it was one of the Toby Roberts ones. I'm not sure where it came from. I can't remember now, but it was covered in iron slime and there was a pinhole corrosion pit in it that had caused its failure. So yes, it can happen, certainly. It did happen.
Yeah. I have another one. Early on, you showed the brickwork with the headers spalling off.
Yeah.
Was the mortar in the job? Was it a lime mortar?
It was lime mortar, and I wish I could find the report that we wrote on it to confirm what the double salt was that precipitated in the mortar. But I think it was basically water drawing, because bricks contain quite a lot of gypsum, which is that efflorescence you see on brickwork, and you can dissolve it off with acid. So I suspect that was being wicked up into the mortar being probably slightly finer pore size. So the water went there, then evaporated from it, deposited this strange double salt. I think it was probably potassium calcium. So
I've got a problem.
not syngenite. Well, yes, you get quite a lot of that sort of problem, but that may be just precipitation of other salts. But yeah, it wasn't syngenite, I don't think, which is potassium pentacalcium sulfate, I think, but it was one of the other ones. I wish I could remember. Somebody will tell me, or I'll find the report.
Anybody else? Oh, yes, lots. Okay. You go to Martin first, please.
Martin Preen, Richter Associates. Great talk, Steph. As ever, way above my chemical knowledge. I've got one question about something you didn't talk about, and that was essentially bimetallic corrosion, which is is that my GCSE level of chemistry? It's one of the most common things that cause problem in engineering. Is that relevant to ground engineering?
I don't do corrosion, so I think the answer is yes, because you're always going to get corrosion when you've got two different metals in contact. I remember when we did Baker Street to Bond Street, where there's acid groundwater there. When we did Old Street, the answer was to line it with stainless steel, and then there were the questions about stainless, and apart from anything else, the unbelievable cost of the stainless. But we tried then to look at coatings for the segments to try and protect them from corrosion. And the problem there, looking at organic coatings, was that things like tanks, water tanks, not Ukraine type tanks, can be coated with sort of plastics and various lining materials. And when you probe the suppliers of these materials, they say, well, generally we can't really give you much guidance beyond about 20 years, and you're looking for 120 years, because most of the structures to which our products are put, like say a tank on a ship or something like that, have been thrown away with, or have a working life of about 20 years. So corrosion protection is quite difficult, but there are a few bridge structures where this bimetallic corrosion or protection becomes a big issue. So I think you need the bridge engineers, not me. But yes, it's of course a massive problem in the ground.
Who's next? Who's the nearest? Benjamin?
Hi, Benjamin Gore from GCG. Thank you, Professor, for such an interesting talk. I would just like to ask a question, because all these reactions are all redox reactions, basically. And would it be possible to, or is there any solutions you have encountered where you intentionally introduce materials or chemicals that are far more reactive, so that you intentionally force the redox to use these materials, such as like a sacrificial metal, as an example, so that we can make these redox reactions more predictable and therefore manageable from that stance?
A very good question indeed. If you like, in some ways, people have been trying to do that for bioremediation of contaminated land, and also, of course, using biology to precipitate calcite for grouting. But I think the difficulty is to keep an introduced population happy in the ground where there's competition from the natural bacteria species in the ground. So if you can create an environment where your introduced species can flourish, then you can do it. But I think that's the challenge, is because they're only going to achieve results if there's an awful lot of them. So you've got to have a big population. One won't do it. Many millions is going to be what's required. But how do you keep that population alive? I'm sure there are lots of cases. Well, effectively, we've done it by introducing grouts, like we did on the caisson to get the hydrogen sulfide and mercaptans. We put in organic carbon. Had we wanted to do that, would it have happened? I don't know. But yes, you could, with taking the examples where it's happened by accident, and then move them into to see if they were useful. Yeah, so that's the challenge to you, to find a useful one where it's happened in practice. Yeah, but it's a good point. I mean, I think that, I mean, certainly the people who are doing the bioprecipitation of calcite for grouting believe there's a great future in it. I think it's a little bit at the moment of an application looking for a problem, but it may be that the application will find it not grouting a ground, but doing something else. I wonder. Yeah.
Chris Menkiti, GCG. Thanks, Stephan, for a wonderful talk. I did try to revise my A-level chemistry, but it wasn't enough. My question relates to the conclusion of your talk, where you were looking ahead at use of recycled materials. And you highlighted that the guidance relates to how sustainable they are rather than the operational use of those materials. So my question is, what is the answer? Do we just have to go through the painful experience of, going through these problems in order to develop the relevant guidance? Or is it something that we could look ahead a little bit of and predict what is the right operational guidance?
Do you know, I'm almost minded to ask you to pass the microphone to Murray on your left there. Murray, I mean, basically, I think we've got to, I believe RAP have now stopped writing guidance on construction materials, is that right? No.
Yes, they withdrew, I think, pretty much completely from, sorry, this is Murray Reid, ex-TRL here, that they stopped completely on the civil engineering the side of things about 2012 or thereby. The focus went much more on to textiles and cloth and things that had a higher sort of carbon footprint immediately. So yes, I mean, I know it's the thing that our reports there. We were involved in a lot of these ones. I don't think we're that one, but I don't know if these are still available anywhere now. This is the difficulty, that stuff that was produced and was readily available on sites such as RAP gets dispersed and isn't easily available. So you end up with people sort of having to start from scratch again and reinvent the wheel.
I mean, it's not that I'm saying one shouldn't use these materials, crushed concrete, IBA, and things like that, but I think we need, as a community, to be aware that they don't come without risks, and that, like with all new materials, it takes a while for us to understand what those risks are. And at the moment, I think, Murray Reid, you make a very good point that who is writing the guidance, and even the guidance that does exist, is it still available? I think we're being invited to use these materials because they're good sustainability credentials, excellent. But, ask ourselves, what do we know about their long-term performance? So we really need some longer term trials, if you like.
I very much agree with that. The difficulty, of course, is keeping any trials going for long enough to get results on them. I've been involved over with recycled secondary materials, and some sites we have managed to go back up to maybe about 5 years or thereby, but it's very, very difficult to get funding and then to get permission for it, because basically if there isn't a problem, people aren't too keen on disturbing it in case they find a problem, quite understandably. Yeah. I think, like many things, it will just, the only ultimate answer is time and experience. We can do lots of durability tests for looking at things in the future. They're mostly mechanical type tests or whatever, which can predict that. That assumes, of course, that there aren't any chemical reactions. And you rightly point out the very high pH that recycled concrete, particularly pure concrete, can achieve, and the effects that can have. Incinerator bottom ash is full of all sorts of things, as again you very rightly highlight, and I very much agree with that. Your point about the aluminium, it all comes just from the cooking foil, the baking foil we all use every day in our homes. What happens to that is very weak. It's in tension, it goes into the flames, and a lot of it ends up in the fines, where it's then very reactive. And particularly if you then take your IBA and mix it with cement, you have got the perfect conditions for expansive chemical reactions on there. They do as much as they can, because that's where they make their money.
Try and get the foil out.
Yeah, you can't get the fines.
Separated at home. not in the plant. They should be separated, you know,
This is our,
individual level.
I've already got 3 bins outside my door.
yes, I'm just kind of, like
That's
most
the
councils,
idea
Eastern
before.
Bartonshire, we have a number of different bins and all that. We have a separate one for. That is one for future discussion, I think. Chris.
Thank you, Murray, for that. We're going to have to, I've got a few notices from both eggs and
Carry on. I took it back.
So whilst I'm sorting out these slides, I'd like to just say thank you on behalf of the audience here and our audience on line. The first one, yeah. Thank you very much again, Stephan. That was fantastic, and I'm sure given lots of people lots of food for thought, certainly me. I got apologies this morning from the BGA chair. This is the joint. Sorry, I haven't introduced myself. I'm John Davis. I'm the chair of the eggs. So apologies for that. So David Toll, the chair of the BGA, and Andrew Ridley, the vice chair, were both intending to be here, but things have happened and they aren't. So they send their apologies. So I'm representing the BGA at the moment to give you these few notices from them. And I think the big one in there is the well, the 2 big ones really are the Rankin lecture in next week, and the first one is the BGA touring lecture, which I guess Martin is not online. That's the point of a touring lecture, is it? I don't know. It's not online, so if you're in Dublin, please turn up. Oh, Belfast, sorry, I missed it. Sorry, that's a proper faux pas, isn't it? And the Cooling Prize is a precursor to the BGA's Georesilience Conference, which the next slide is about, in Cardiff, in a few weeks' time. And that almost clashes. Sorry, no, one more slide before we get to that. We have the European Conference on Soil Mechanics coming up. If you want to put a paper in there, then please get in touch with the BGA before you do that. And then almost clashing with this, with the BGA conference in Cardiff, is the engineering group conference. And I've put this one in second, so you remember it, because that's my privilege tonight. There are still spaces available here, but not many. So if you're interested in these subjects, please book soon, or else you'll miss out. It's usually really, really good fun. Very quickly, I'd also encourage you to go to this. So this is here at Burlington House in a few weeks' time. So the current president of the Geological Society is an engineering geologist, Ruth Allington, and I've seen a good chunk of this this presentation before, and it's very thought-provoking and well worth attending. So this is a public lecture here, unusually. So you do need to register through that Eventbrite site. So if you go to the JOSOC website, you'll find this page and you can join. Almost last in terms of events. This event is a sort of co-badge thing between the eggs and the Quaternary Research Association Engineering Group, of which I'm a representative of, I suppose. And this is a free one-day conference in Birmingham on basically Quaternary engineering geology and high-speed 2, but you don't have to be involved in high-speed 2 to go. I recommend all of these QRA eggs events. All the ones I've been to so far have been absolutely fantastic, very thought-provoking again. Martin, this is especially for you. This is the date now confirmed just a few days ago for the next Glossop medal presentation, Thursday the 23rd of November this year. So please put that in your diary. We haven't got a excuse me, we haven't got a title from John Cripps yet, but it will be related to mud rocks. And related to that is Glossop Award, and this piece of information will be publicized over the next few days, but we basically have a set of questions now if the early career engineering geologists want to enter, and we're linking this back to the conference and to sort of Peter Fuchs themes of that conference. That's all the slides of interest to the people online. But we haven't been able to have a drinks reception tonight in here for all sorts of reasons that are too tedious to go into. So if people in the audience want to go to the pub, that's how you get there. So thank you very much, everybody. That's the end of this meeting. So we need to, we are just about Thanks, Kevin. We are just about done now. Kevin,